The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Welcome to today's webinar, Line Differential Protection Fundamentals. My name is Tracy Noble with ABB Power Systems, and I will be moderating today's event. Before we get started, I wanted to go over a few housekeeping items with you. All participant audio will be muted during the event today. If you would like to ask a question, please use the question box or the chat box on the GoToWebinar control panel on the right side of your screen. We will answer as many questions as possible throughout today's live event. Today's webinar is being recorded, and the link to the recording will be emailed to you following the event. Actually, tomorrow, the link will be mailed to you. Feel free to forward the link on to people that you know will benefit from the presentation. And now a message from our legal department. ABB is pleased to provide you with the technical information regarding protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's web-based protective relay school, you agree that ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose, and ABB is not responsible for any action taken in reliance on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Contact an ABB sales representative for further information. Today's webinar is Line Current Differential Protection, and our speaker today is Imran Rizvi, and we would like to thank Mr. Rizvi for stepping in. We had to change speakers at the last minute, and you're going to love him. He's great. I'll tell you all about him. Imran Rizvi graduated from University of Engineering and Technology in Pakistan and got his BS in Electrical Engineering with a specialization in power systems in the year 1990. In that same year, he joined WATSA Pakistan, which is an electric utility, and served as transmission and distribution engineer until 2000. In 2000, he joined Siemens Energy and Automation and worked in both Saudi Arabia and Canada until 2008. In 2008, Imran joined ABB Canada as Regional Technical Manager for East and Central Canada regions. And now it's my great pleasure to introduce Imran Rizvi. Take it away, Imran.
Thank you very much, Tracy, and welcome all of you on our webinar for line differential protection. The objective of this webinar is to know the fundamentals of line differential protection. We will talk about current differential relays. We will also talk about line current differential relays, and then we will have some application issues addressed in this presentation. The agenda for this webinar is that first of all, we will start with the introduction, and then some words about differential protection in general, and then we will be specifically talking about line current differential relay, and then application issues, and the important part of line differential protection is obviously the communication of that, so we will talk about that. And then at the end of the presentation, we will summarize the important points. So line differential protection, so this is the basic idea of line differential protection. You have station A and station B, and between that you have a transmission line, you have two breakers, one breaker on the substation A side, another breaker on the substation B side, two CTs connected on each side of it, and line differential protection box connected to this CT at station A, and then another box connected to this CT on the station B side, and then these two guys will talk through certain communication medium to exchange information about the analog and sometimes the digital data, the binary data for these two relays. So that's the basic idea of line differential protection. So what are the elements of line differential protection, multi-terminal line differential protection? So it is essentially a unit protection. So when we say about unit protection, so all the differential protections are normally unit protections, and they are inherently very selective, and the boundaries of the protections are defined by the location of the cities. But still, in the let's say in the ideal world, that would be that there shouldn't be any problem of discrimination of the fault between within the protection zone and out of the protection zone. But that would be an ideal situation. But in practical terms, there are several scenarios in which to identify whether the fault is within the protection zone or out of the protection zone, it might be a little bit tricky. So to determine whether the fault is within the protection zone or out of the differential protection zone, that is a task, and then we will talk about it in detail, that what type of techniques we use in ABB protection relays to determine whether the protection is within the zone or out of the zone. In line differential protection, you can have obviously an element of an equipment transmission line which needs to be protected, but also in certain cases you have the power transformer within the protection zone as well. So having a power transformer within the protection zone of line differential protection imposes some more issues, and those issues need to be addressed, and we will talk about it. What it essentially does, it measures the currents at the terminals of the protected circuit, and then transmits the information about the currents to the remote ends. I mean, if it is two line ends, then we have one remote end. If it is more than 2 up till 5 line ends, our ABB line protection can handle. So we'll have 4 other remote ends. And also it compares the currents using the classical differential protection principle. And then, of course, we have to supplement that current differential principles by some additional criteria to cater the needs of specifics. And inherently, this differential protection, line differential protection, is highly dependable. And when we say dependability, it means that it will operate for all the intended faults for which this relay is intended. And it is also highly secure, which means that it will not operate for the faults which it's not intended to. So, so this is something which is these are the two terminologies which are normally used in the protection world quite often. Also, this line differential protection is quite good for evolving faults as well as for cross-country faults. And unlike distance protection, line differential protection is immune to power swings, mutual coupling, and series impedances unbalances. Because of this numerical technology, now we can transmit the sample data, and therefore we can calculate the sequence components as well as the harmonic components of the measured analog values. So right now, as we talked about it, that this is the local station, we have to define in line differential protection scheme that what is the local station and what is the remote station. So this is the box which is measuring the local current, and it is getting the information from the remote and relay, and then it is processing the information in this box. So there are different topologies, and we will talk about it, different way of communication, that also we will talk about it. But the basic idea is that the box takes the information locally, and then it takes the information remotely from the remote end, and then processes the information and compares it with the threshold values to get into a decision of tripping or not. So as this line differential protection is basically a current-only scheme, so there is no dependency on the VTs. So it means that we do not have to worry about the fuse failure protection and CCVT issues or power swing issues. Yeah, VTs can be connected in line differential protection scheme, but just for the measurements purposes, or but the main line differential protection does not really take care of the voltage information. And it can be very, very sensitive in detecting the ground faults. And we will talk about it, that how we can really detect very sensitive ground faults as well by using this line differential protection scheme. As it calculates the values and the differential as well as the stabilization current values per phase, so that's why the information is phase segregated, and it is then ideal for the evolving faults as well as for the cross-country faults. And then as we have the measurements on phase segregated basis, so that's why we can have single pole tripping as well. And because it is not dependent upon the measuring of the impedances of the line, so that's why the series compensated lines will also have no impact on the line differential protection scheme. The only disadvantage of line differential protection scheme is the communication part of it, that if we lose for some reason communication, then we will lose the line differential protection, and then we'll have to fall back on some other types of protections like distance protection, or maybe in some cases just the overcurrent or feeder protection only. So, but with the advancement which we are making in the communication technology, this line differential protection is becoming more and more popular as compared to, for example, distance protection. But in high voltage or extra high voltage lines, of course, both of these protection schemes are used, with main as line differential protection and backup as distance protection. Types of current-only schemes, current differential can be analog or digital, and you can compare the phases as well, but that's something which is not really popular nowadays. So we will move on to the next slide. So here we have this current differential diagram. As you can see from here that IL is the local current, and if CT is connected with this dot notation, then if the current is flowing in this direction, the CT secondary current will be flowing in the other direction, and then IL is moving from here to here, and then IR is the remote current direction. And with this current notation, dot notation, then IR is moving in this direction. And the relay operating coil is in the differential path of these two circuits. and as you can see that IL plus IR will flow through the operating coil of this differential protection relay. And this is the protected object, and that protected object can be transmission line in case of line differential protection, or in case of other protected equipment like transformer or anything like that. So that would be the protected object. But basically the idea of differential protection is the same. So this would be the ideal situation, and when these CTs are actually have the ideal characteristics. So in this case, if the fault is external, then if the fault is somewhere here, external, then the direction of IL will remain the same, but the direction of IR will reverse, 180-degree opposite. So in that case, IL will be equal to minus IR. So therefore, if we add up these two currents, then the resultant would be 0, and therefore there will be no trip. This is the local current, and remote current is 180-degree opposite. So if we add it, these two diagrams, so then we will result into a 0 differential current. So there will be no trip. But in the other case, if the fault is internal, like the figure shown over here, if the fault is somewhere here between these two CTs, then in that case the algebraic sum or vectorical sum of both these IL and IR will flow through the operating coil of the relay, and then relay will operate. So there will be a trip. So you can see the local end current oscillograph and remote end oscillograph, they are both the same, so they will add up, and it will not be equal to 0. They will add up and have to have a certain value, and therefore tripping will occur. So that was the ideal situation if the CTs are behaving ideally as per their characteristics. And that would be in the operating and restraining region, IL over IR, so that would be -1, and that would be in the restraining point. So in this case, we will have a very high security for the external faults, and at the same time, very high sensitivity for the internal faults. But because of the fact that we do not have the ideal situation, and there can be some errors, and we will talk about it in detail about these CTs. So therefore, we have to introduce the restraining winding also into the differential scheme, which will provide more stability to the differential protection scheme. So we will have to add these two restraining coils into the circuit. In that case, what will happen is that the same differential current will flow from the operating coil, but it will have an additional restraining currents, which will improve the stabilization. So the tripping will occur only if the vectorical sum IL plus IR is greater than or equal to the absolute values of IL and IR together with the K factor. So K will determine the slope of the characteristics. So here is the operating and restraining characteristics. As you can see from here, that if the operating per unit operating current is on the y-axis, and on the x-axis we have the restraining current in per unit of I base, then the dual characteristics will look like in this fashion. Anything above this characteristic line would be the tripping area or operating area, and anything below this characteristic line would be the restraining area. But in the case of that was the line, that was the differential protection which we were talking about. But in case of line differential protection, because the two relays are physically separated by several, or in some cases hundreds of kilometers, so we have to have a communication link between these two boxes, 2 or 3 or 4 boxes or 5 boxes in line current differential schemes. And we have to exchange the data measured locally and measured remotely to come to some tripping conclusions. So in that case, half of the operating current will flow in the, let's say, local box, and half of the operating current will flow on the remote box. Here you can see that in normal conditions or external fault conditions, you can see that these two currents are exactly opposite to each other. So they are forming the operating current equal to 0 and therefore no trip. And in this case, these two currents are in phase and therefore depicting that this fault current is for the internal fault and therefore will get a tripping. So this is the line differential characteristics. Here we can see it's the same, essentially the same characteristics which we have seen before in the earlier slides. But some additional information is mentioned in here. So it starts from slightly above the origin, and this margin ID min, or the minimum differential current value, this is also a setting in RED 670. RED 670 is the line differential protection device. So it starts a little bit higher than that of the origin, and that is to cover the inherent inaccuracies of the CTs, and then it ends. It has actually 3 sections: Section 1, Section 2, and Section 3. And these sections are defined by some settings which you can do it in RED 670. First setting is the ID min, as we talked about it, and that is to compensate. It is to compensate some inaccuracies, inherent inaccuracies in the CT circuit, and therefore we have to desensitize the differential protection to that extent. And there is another setting which is the endpoint of the Section 1, and then this is the second section, and this section is actually to cover the current dependent inaccuracies in the CT circuit, and that is also defined by 2 settings. One is the slope of the Section 2, and then the endpoint of the Section 2. And then there's a third section which is defined by the slope as well as the starting point, which would be the end of the section number 2, and it will go on. So anything above this characteristic line would be a tripping area, and anything below would be a stabilized area, so no tripping. And you can see there's another dotted line over here, which is ID min high, and that we will talk about it in the later section of this webinar. I will right now will talk about this continuous line, which is the unrestrained limit, and that is the limit, if the differential current is high above that particular line, so then it will not be restrained by any conditions. So it will operate, it will give out the tripping unconditionally. And this is to cover those high faults, very high current faults. And there, the differential protection should not really care about the restraining quantities and should operate unconditionally. So that's the general idea of this line differential protection characteristics. Now let's talk about it. How many types of line current differential relays we have, or we had it. So some of you might remember those pilot wire differential relays. So those were the first generation of line current differential relays, and those were used for not very long lines, but for short lines or medium lines. So let's talk about it. That what is the pilot wire line differential relay? HCD is the relay in ABB product portfolio to cover the line pilot wire line differential protection relay. So basically, this relay was working in this manner, that you have these 3 CTs with all these dot rotations, and those 3 CTs were being fed to a sequence filter. And this sequence filter, the job of this sequence filter was to produce an equivalent voltage, which is equivalent to the positive sequence, negative sequence, and zero sequence currents of this side of the line. And in the similar fashion, on the other end of the line, there was a sequence filter and corresponding VH, let's say, voltage was created. Just a moment. Sorry for the interruption. All right. So we were talking about that in both line ends, we were having these sequence filters, and those sequence filters were providing the equivalent voltage VG or VH, and these voltages were resulting into a pilot wire current, which was flowing through this path in the through fault conditions. Whenever there was a through fault current or through current, so these voltages were creating this current, generating this current in such a manner that there was no current through the operating coils, and the current was flowing only in the restraining coils. But in the case of the internal faults, the voltage direction was opposite, and then it was forcing the currents through the operating coils, and therefore tripping was the result of this these currents. So that was basically the idea of pilot wire line differential protection. So, but there were some problems associated with the pilot wire use in these schemes. and those were related to the station ground potential rise, as well as induction from the power line circuits as well. And because of those problems, we were having troubles in and maloperations in the pilot wire protection schemes. And those maloperations were basically that if, for example, somehow the pilot wire breaks in some area, or there is a break happening in the pilot wire. So in that case, the full current which was flowing through this circuit will start flowing through the operating coil, and that will result in erroneous tripping. Similarly, if, for example, there is a huge capacitive charge, capacitive current, so then there will be a short circuit right here or right here, and then the operating coil will have no current, even if the fault was inside the protection zone. And similarly, if the line and these pilot wires are too long, then they can actually, again, you will not have any operation because the impedance was too high, and that would be like a problematic situation. So because of these inherent problems in pilot wire differential protection schemes, these pilot wire protections are not really used anymore in the new installation. There were some solutions also which were taken to avoid these problems, as we talked about it, and those were like twisted. We used to twisted wire pairs, or there were some gaps or arresters, drainage reactors, and neutralizing reactors to compensate for the capacitance. And but still, for all the new installation, these pilot wire relays are rarely used. So one was the situation that okay, we have gone away from the metallic communication. So non-metallic communication also, like wireless, has also some disadvantages, and which are, for example, signal corruptions or propagation delay, time synchronization. So these were the problems. These are the problems for the non-metallic communication. So the basic idea was to use the metallic communication, but with the fiber optics. So right now, most of the line differential protections, they employ either direct fiber optic or through the telecommunication networks. With the advent of the numerical relays, now we can actually calculate the harmonic analysis, as well as we can calculate the sequence components, and that really gives us an added advantage in calculating the line differential protection quantities. So because in segregated phase differential protection, we have to really communicate a large amount of digital data to be exchanged. So therefore, the channel requirements are also quite stringent for line differential protection, and we will have a discussion about those requirements later on in this presentation. Direct fiber can be used short range, 1 to 3 kilometers, and we can use a medium range direct fiber with a different requirement from 3 to 50 kilometers, and then long range. And we can use G703 and MUX also we can use for the communication between the line and relays. Now let's talk about the line termination. So we can have line differential protection scheme involving one breaker, for example, or we can have a ring bus or a breaker and a half scheme, or we can have a transformer also in the protection zone. And for each type of line termination, we have specifics which needs to be taken care of. So let's say we have a single breaker scheme, and here that would be a very simple stuff, that we have just one breaker, and we have a line current, and ILS would be the secondary current feeding into the line differential relay. So that would be the case for single breaker. But what if we have a 1.5 breaker scheme or a ring bus scheme where we have two breakers, as it is shown in this this diagram. So you have one breaker over here and the other breaker over here. That's your transmission line. And if IL is the current of the transmission line, the IH is flowing from here, and the rest of the current IL minus IH is flowing through this breaker. So there are two CTs which are going to the relays. So the question arises that how we should connect these CTs. One option would be to connect these two CTs directly to the relay, and the relay let the relay do the math, or the other way is to parallel these two CTs and then feed the resultant current to the relay. So there are some advantages for using these two CTs and connecting directly to the relay instead of paralleling it before the relay, and we'll have a talk about that. So this would be the classical way of connecting these two CTs and then the resultant feeding into the relay. But this scheme has a little bit of disadvantages, and those disadvantages would be that if the CTs are connected in such a way, in this way, then we do not have the individual CT information to the relay, and therefore we will lose some metering information. For example, we will not be able to find out the individual current transformer health regarding, let's say, open circuit or shorted or saturated conditions, for example. We will not know it, and in certain cases larger restraint current will be required, which means that we have to desensitize the protection line differential protection settings, and this is because of the fact that in the ideal case, if the CTs are ideal, then you really, this point of desensitizing the differential setting will not really matter. But in the practical case where the CTs will have definitely some errors, then in that case there will be a differential current equal to the errors of these two CTs feeding into the relay. And to compensate that differential current, then we will have to desensitize the relay settings, and it means that we will need more stabilizing current, and then therefore we will have to raise the characteristics of the differential protection scheme. So that is the disadvantage of connecting these two CTs before it is connected to the relay. So as you can see from here, that if the CTs are separately connected to the relay, separately fed to the relay, then the characteristics would be the same point would be here. And if it is connected in parallel outside of the relay, then we have to desensitize the protection settings. So the best way is that we have to feed the relay these two CTs separately. And in ABB line differential protection, RED 670, you can do this thing because we have very flexible CT inputs, and up to 8 CTs can be fed into one box. So we have lots of options available to connect these CTs separately. Now let's talk about the case when we have power transformer inside the protection zone of line differential protection scheme. So because of this transformer, then we have to consider certain aspects, certain technical aspects, and to take care of the transformer specifics. So first of all, we need to know about the current phase shift across the transformer. Then we have to take care of the transformer inrush current, because the transformer inrush current will be felt by this CT, but not by this CT. So therefore, to avoid the incorrect behavior of line differential protection, we have to take care of certain measures to filter out this inrush current. And also, we have to take care of the vector group of the transformer as well, because if, for example, this side of the transformer is connected in Y and grounded, then any fault over here will actually create the ground fault current, which will be felt by this CT, but not by the remote CT. And then again, we will have unwanted trip. So we want to avoid this thing. So we have to take care of certain measures like zero sequence current elimination to avoid this kind of situation. So this diagram actually shows you the situation for the inrush current. So as we can see over here, that if this is the local station, then inrush current is being is felt over here, but not on the remote end. So therefore, we will have a trip, unwanted trip, which we really need to avoid. So the way how it is done is to filter out second harmonic component of the current, and if it is more than that of a certain threshold value, which is a setting in the line differential protection scheme. So if it is more than that particular setting, then the differential protection will be blocked for that particular period of time. Similarly, if we have a delta Y transformer and we have Y grounded on this side of the transformer, then any fault, any ground fault on this point would actually result in zero sequence currents, which will be circulating in this direction and will be felt only on the remote side, but not on the local side of the line differential protection scheme. So therefore, we need to do this zero sequence current elimination to avoid this kind of situation. Previously, it was done by using the auxiliary CTs, But now it is done numerically, because all these numerical relays, they can calculate these currents in the proper way. All right, so there's another situation when we have a tapped transformer over here, and in some cases, just to for economical reasons, we have a tapping of a transformer, and there is no metering, there is no measurement from this tapped line. Still, line differential protection scheme with RED 670, we can protect this tapped line as well, and we will see that how it will work. Let's say we have a fault over here. So in this case, we do not want to get a tripping on this line differential protection scheme. Actually, we want that the protection, downstream protection, should take care of this fault, and that is done by a certain measurement. Certain measures are taken in RED 670 to avoid this kind of situation. The criteria which is used to detect the faults in the tapped line on the secondary side of the tapped line is that the fault level on the secondary side of the transformer is quite low as compared to the fault level on the transmission line. So, which is shown over here. So that's your line fault current, and this is your transformer secondary fault current, which is quite less. So we use this criteria to get the protection of the tapped lines without even measuring the tapped line current. And how it is done? It is done in such a way that a time delay differential function is introduced with a high limit ID min high. So that is the dotted line which we saw before in our when we were discussing the characteristics of the differential protection scheme before. So that is the limit ID min high, which is used to detect this kind of transformer faults. So a time delay is introduced whenever the current is detected in this situation. So we can see from here that the protection zone for the tapped line is still intact, and any fault on the secondary side of the transformer would be detected by the local protection over here. So these are the settings which you can do for RED 670 to detect the faults on the small transformer. And what we can do is that we have to put a value of ID min high, as well as we have to put a delay of, in this case, the delay is the inverse time characteristics has been chosen, and the time dial is 0.3 and the K factor is 0.2. So this type of protection can also be used in some specific cases where we have a small tapped power transformer in the transmission line. High impedance faults are also one of the things which are very difficult to detect because of the fact that the ground fault currents are very low, and but as we know that the numerical relays can calculate the negative sequence current, so we can actually use that feature to detect those high resistive faults and can take care of these faults effectively. So as over here you can see that if a high resistive fault is at this point, so this will act as a negative sequence source and the currents will flow out of this fault point. So if the currents are flowing, these negative sequence currents are flowing in the same direction, then the fault is internal. And if the two currents are flowing in the opposite direction, then the fault is external. So the local current phasor is taken as a reference, and the remote current is taken as will be compared with the local current, and the angle between these two measured phasors for the negative sequence currents will be taken into account to find out the direction or the location of the fault. So if the fault is inside the protection zone, then these two or three, in case of three terminal lines, all these phasors will be in line together in the same direction, and the current and the relative angle between the local current and the remote current will be equal to 0 or a little bit more than that. So then this region, these phasors will be falling in this region, and that is the internal fault zone. And if the fault is outside the protection zone, then the phasors will be falling in this region of the fault discriminator, and the fault will be declared as outside the protection zone. There's another factor which is quite important in line differential protection scheme, and those are the charging currents of the high voltage transmission lines. And this is the pi network for a transmission line. So that's your local end, and this is your remote end, and a charging current will be flowing as and it will be detected as a differential current for the differential scheme. So in RED 670, what it does is that in the normal conditions, it measures the charging current and then subtracts it to make the resulting differential current equal to 0. So in this way, we know that how much is the charging current, and then that charging current is subtracted from the differential current to make it a 0 reference, and this way the compensation for the charging current is done. In the case of three terminal lines, we will have one box at each station. So we will have three boxes, RED 670, connected with the transmission communication lines. And the currents from all the terminals will be calculated and transmitted to the other for the calculation of the differential as well as stabilization quantities. In case of 5 terminal lines, then we will have 5 boxes, and each box is connected to the other one, and and the decision is made depending upon the topology of the network, communication network. In the 3 terminal lines right now, you can see that this topology for the communication can be used. And in this particular example, we will have 4 communication modules. We call it LDCM, line data communication modules. And now you can see by using these 4 communication modules, all the relays are actually talking to every other 2 relays, each other 2 relays. So, for example, this local relay is talking to this relay as well as to this relay. And similarly, this particular relay is talking to this relay as well as to this relay. So this is a very nice redundant communication network which you can create by using these communication modules. If one of the link break, for example, then it will automatically reroute the communication network. Now, there are 2 ways for time synchronization in RED 670. One is the eco method, and eco method is that it is used only when there is a delay symmetry. Delay symmetry means that the time taken to send telegram and the receive telegram, if that both are same, then it means that they have the same delay symmetry. So this is used, delay symmetry, eco method is used when the delay symmetry is there for time synchronization. But if that is not the case, then we recommend to use this GPS time synchronization. We can have a redundant, 100% redundant communication channels. One channel can be dedicated as a primary channel, and the other channel can be dedicated as secondary channel. And if something happens in the primary channel, then after a set time delay, it can switch to the other secondary channel automatically. There are 2 types of communication topologies which we can use. One is master-master scheme, and in master-master scheme, it means that each relay is connected to each other relay. So as you can see at station, let's say A, this relay is connected to each of the other 4 relays, and similarly, all other relays are connected to each other. So that's really a very safe communication topology, and if some communication link breaks, still the line differential protection is intact, and it falls back to the master-slave system. As now you can see that all these 5 terminals, they are exchanging information, and each box in this master-master system will make its own decision for the tripping and own decision for the differential and the destabilization current. In this master-slave system, only one box is acting as a master, and it is fetching all this information from the all other 4 devices. And the tripping decision is done by the master, and then it is transmitted via this fiber optic link or the communication link to the other terminals to trip the circuit. So both of these master-master as well as master-slave systems, they are used, have their own advantages and disadvantages. In master-master-slave, master-master system, you have more redundancy, whereas in master-slave system, if any communication link breaks, then the line differential protection scheme will cease to exist. But in master-master system, the amount of fiber optic links and fiber optic cabling is much more than that of in master-slave system. So, but there is one very nice application example for master-slave system where actually you can use two different types of relays: RET, which is dedicated transformer protection relay on one end, and RED, which is line differential protection relay at the, on the other end. So this relay can take care of the transformer protection, as well as it can provide all the information, current information, all the current information, and transmit it to the RED 670. And RED 670 can take the role of master for line differential protection scheme and take care of the decisions for this transmission line protection, whereas RET 670 can take care of the transformer protection itself. So master-slave scheme is also has its own application advantages. RED 670, as we said, that this is the line differential relay from ABB, numerical relay, and this has got this protection functions, which you can see it that it is not only includes the line differential protection, but also it has a backup distance protection as well, in addition to breaker failure and all other protection functions. Rely On is a brand name of ABB protection devices, and RED 670 is the line differential relay, and Rely On is efficient substation automation for protection, monitoring, and control of high voltage overhead lines and cables, and it is delivering significant savings in configuration, setting, erection, commissioning, maintenance, and space, improving availability with outstanding performance and efficient information management, enabling applications with multiple algorithms, multiple objects, integrated and distributed architectures. Application flexibility makes them an excellent choice for both new as well as retrofit installation. Thank you very much for your participation. Shortly, you will receive a link to an archive of this presentation. To view a schedule of remaining webinars in this series or more information on ABB protection and control solutions, visit our website www.abb.com/relyon. At the end, a disclaimer: ABB is pleased to provide you with technical information regarding protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's web-based protective relay school, you agree that ABB is providing this information to you on an informational basis only, and makes no warranties, representation, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose, and is not responsible for any action taken in reliance on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Contact an ABB sales representative for further information. Thank you very much for this webinar, and now we will open for the question and answer session. Tracy? So let us see what we have. Questions in the chat box. There's one question about would you provide highlights of the line distance protection and compare it with the line differential? Well, during our presentation, during our webinar, we have been talking about the advantages and disadvantages of line differential protection scheme as compared to the line distance protection. So basically, because of inherent advantages of the differential protection schemes, we really get a very highly dependent as well as selective protection due to line differential protection. But in distance protection, you know, whenever we have a typical situation like series compensated lines, or we have a transformer inside the zone of the protection, then we really get a little bit of trouble of calculating the impedances, and therefore it may or may not be very suitable for as a primary protection to that transmission line. Whereas in line differential protection, as we are just measuring the currents and we are not measuring the voltage, or we are not calculating the impedances, so therefore we really rely on the current information, and therefore it's very, very selective protection. And but the disadvantage of line differential protection is that we are depending on the communications, and if somehow communication breaks down, then we do not have line differential protection at all. So that is the main disadvantage. All right, so there's let me just go through the okay, so there are some questions about the settings. So I would suggest that somebody is suggesting the section of the manual of this RED 670. So I would say that for settings, we generally, I mean, we provide some recommendations in the manual, in the technical reference manual or an application manual, but for particular cases, then we can discuss those settings case by case. So you guys can contact us on our email or something like this, and then we can discuss about the settings issues. Another question is that line differential protection practical on MV lines such as 33 kV. Also, what are practical cost efficient communication options? Well, the most economical solution would be a direct fiber optic link between the two ends or three ends, and up till 150 kilometers you can actually use a direct fiber optic link. And if the distance is more than that, then you can use the repeaters, for example, or you can use the other communication medium like G703 or X21. So those can also be used. But as far as the cost-efficient communication as well as it is concerned, so I would say direct fiber optic would be the best solution if you see the cost as well as the technical advantages of having a direct fiber optic. Another question is that how we select these slopes in the characteristics. Well, normally the recommended slopes are actually work quite well. In fact, in differential protection schemes, almost all the default settings can be set as it is, and in 90% of the cases it will work. But of course, I mean, if you want to change those slopes, there is an option for that, and you can actually change the endpoints as well as the slopes of the characteristics, and it depends upon your power system requirements. There is another question, how to compensate the inrush current to prevent the false tripping of line differential. Yeah, so differential current, the inrush current is characterized by the second harmonic, and all the differential protection relays, they filter it out, the second harmonic, and then block the tripping as we discussed during our presentation. Another question is line differential protection practical on MV lines such as 33 kV? Well, line differential protection can be used in any voltage level. In fact, I mean, whenever it comes to protection, it really doesn't matter at which level you are using, like line differential, or even you can use at 33 kV a distance protection as well. It only depends that what is your protection philosophy, and how much is the length of the line. If, for example, it's a very short line, then you might have only choice to get the line differential only, because distance protection will not work properly for very short line. So line differential would be the only choice for you. And yeah, but it all depends that what is your protection philosophy, regardless of the voltage level. Is there any question which is missing now? Tracy, are you there?
Yes, I am. Oh, we just got another. What is the range of inrush currents enough to prevent trip during the startup of power transformers? Are there any standards about it?
Yeah, it depends upon the transformer characteristics itself, that how well it is designed, and normally 7% or something around that percentage of the second harmonic is present for, and it also depends upon the size of the transformer. So better check with the manufacturers of the transformer, and then you can have a setting for the second harmonic percentage blocking. So that's how normally it is done.
Okay, I think there might be a few questions, but they've gone off my screen and I can't seem to get them back. So if we haven't answered your questions, we will respond by email, because I know there were some that were early on that I can't seem to get back to. So thank you so much. We appreciate your participation. There's a webinar next week as well, and information will be in the follow-up email that will come to you tomorrow, again with the link to this recorded webinar. Thank you so much for your participation. We appreciate your support of the ABB Protective Relay School webinar series and hope to see you at the next webinar. Bye-bye.